Welcome to our discussion on trigonometric identities and equations. As always, feel free to fast forward until you see this slide designating the topic that you want to review. Let's begin by looking at some identities. We already know the simple ones. We know that cosecant, right, is 1 over sine, secant's 1 over cosine, cotangent's 1 over tangent, etc. We know that tangent is sine over cosine and cotangent is cosine over sine. Those should be in your back pocket. Here are the new ones. I wouldn't worry so much about learning the even and odd identities, although they can be very helpful. The ones that are extremely important to know. This one, of course, is hugely important, used a lot. And then the other two just derive from this one. So if you want to memorize them, that's fine, but they just come from the original one, right? If you take sine squared plus cosine squared equals 1, and then divide everything by sine squared, look what you get. Sine squared over sine squared is 1. Well, cosine squared over sine squared is cotangent squared. And then 1 over sine squared is cosecant squared. You just got that identity. Look what happens if you start with sine squared plus cosine squared equals 1 and divide everything by cosine squared. Well, now you get sine squared over cosine squared, which is tangent squared, plus 1, right? Equals 1 over cosine squared, which is secant squared. That one. So both of those just derive from the granddaddy, sine squared plus cosine squared equals 1, which is really just Pythagoras' theorem of a squared plus b squared equals c squared, because remember, these things come from, on the unit circle, the radius is 1, cosine is this distance, sine is this distance, and so by Pythagorean theorem, we know that sine squared plus cosine squared equals hypotenuse squared, which in this case is 1. 1 squared is 1. So it all comes back to Pythagoras. If you can just remember Pythagoras and remember your little trig triangle, then it's all built on top of that. Okay, with that said, you're going to see a bunch of examples where we can use Pythagoras' theorem and all of these identities to solve for other trig functions given one trig function. But guess what? You don't have to memorize these trig identities, and you don't have to use these trig identities if you just always go back to your simple trig triangle, right? Here's my theta. Remember your SOHCAHTOA. Sine is opposite over hypotenuse. Cosine is adjacent over hypotenuse. Tangent is opposite over adjacent. And then, of course, you just have to remember that, cosecant is 1 over sine. Secant is 1 over cosine. And, of course, cotangent is 1 over tangent. If you have that stuff memorized, which should already be pretty much in your back pocket at this point, then you don't need to memorize all of this new stuff. It's not something new. It really just comes back to this. Because if they tell me cosine theta is negative 5/13, well, I know that cosine of this theta, right, cosine is adjacent over hypotenuse, so this has to be adjacent over hypotenuse. Therefore, my adjacent has to be 5. My hypotenuse has to be 13. Using Pythagoras, we can solve for this side as 12. It's a 5, 12, 13. And now we know every single trig function, because sine of theta, opposite over hypotenuse, 12 over 13, right? Tangent, opposite over adjacent, 12 over 5. And then these are just 1 over them, right? If sine was 12 over 13, then cosecant is the reciprocal, 13 over 12, etc., etc., etc. You get the idea. All you have to worry about then at this point is which ones are negative and which ones are positive, right? Because they tell you that theta is between 0 and 3 pi over 2. So here's 0, here's 3 pi over 2. Theta is down in here. So we're down in this quadrant where cosine should be positive, right? That's because it's not between these 2 points in this direction, it's between those 2 points in this direction, right? It's always counterclockwise. So theta is any angle between 0 and all the way around to 180, 270, right? Anything between 0 and 270. If cosine is negative, then we know that technically theta has to be over here, right? Really, theta has to be between pi and 3 pi over 2, and I just realized that I mistakenly saw that in my mind's eye as 0 to 3 pi over 2, and I've just proven my point that we now know that it's between here and here, right? Pi and 3 pi over 2. So we're down in quadrant 3, and if we're down in quadrant 3, then we know that cosine is negative, right? Sine is also negative, and then everything else builds off of that. Tangent is sine over cosine, so it's going to be positive. Cotangent's 1 over that, so it's going to be positive. And then, of course, 1 over sine and 1 over cosine are both going to be 1 over a negative. They're also going to be negative. Okay? So don't bother trying to learn a whole new technique to solve these when you already have it handled if you know SOHCAHTOA and your simple trig triangle. Here's how they're showing you how to do it with all of these identities. Don't even bother. It's more brain power that's not necessary, right? Again, they're showing you how to do it with all of these identities, and it's not necessary. With this example here, they're starting over with 3s and 4s, but it's the same idea, right? We could still draw a triangle. If we were given one piece, we would know if this is theta, sine being 4/5, sine is opposite over hypotenuse. This has to be a 3, right? There's my 3, 4, 5 right triangle. And now all of these are built off of this triangle, and you just have to pay attention to plus and minuses based on what they told you. Okay? Simple stuff. How about simplifying a complicated trig expression? There are some rules, I shouldn't say rules, there's some guidelines that can help you with these. It boils down to the first thing you want to do is try to use those trig identities whenever you can, and start with the most complicated side and kind of simplify it. Now that only helps if you have trig equations, something equal to something. Here they want you to just start with something and then rewrite it. And in this case they wanted you to write cotangent plus tangent plus blah 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 in terms of sines and cosines. Which makes sense because everything is built on the back of sine and cosine. Everything can be written in terms of sine and cosine. They are the two building blocks of all trig stuff, which is why I kept telling you from day one, really learn sine and cosine because everything builds on that. So, cotangent, of course, cosine over sine. Tangent, of course, sine over cosine. Cosecant, 1 over sine. And last but not least, secant, 1 over cosine. And then you just clean it up, right? You notice that this last piece is going to have a denominator of sine times cosine. So in order to add all these fractions, they have to have common denominators. So you're going to multiply this one top and bottom by sine, so you can get sine cosine, and then this one top and bottom by cosine, so you can get sine cosine. And that's why you have cosine squared here, sine squared there. There's my 1. Cosine squared plus sine squared plus 1. And then we remember that that's our trig identity of equal to 1, right? So you plug that in, and now you just have 2 over sine cosine. Don't know why this is considered simpler. Well, it's considered simpler because it's not a bunch of things being added together, it's just one term, which is simpler, and it is helpful. Because what if you wanted to, let's say, take this and solve for, when it's equal to 0? Well, now that you have this equal to 0, you know that the answer is never, right? That can never equal 0. Or what if you wanted to figure out when this thing was undefined? Well, now you know it's undefined whenever the bottom is equal to 0. So it's undefined at whenever we have 0 and pi over 2 and then multiples, right? So it is simpler, it is nicer to have it all in one term. How about if we try and prove that an equation is not an identity? Well, it's kind of similar as if you need to prove that it is an identity. If you're trying to prove that two things are, equivalent or not equivalent, the easiest thing to prove is that they're not equivalent, because you only need one case for them to fail, right? If you plug a number in and the two sides are equal, that doesn't prove that they're always equal, it just proves that they're equal for that one particular x value. However, the converse, if you can plug at least one x value in and show the two sides are not equal, then you know that the two things are not always equal, right? So it's really easy to prove that things are not an identity. All we have to do is plug in some numbers and see. And of course, the easiest numbers to work with when we're dealing with sines and cosines are zeros and ones, especially zeros. And for all of our trig functions, really, 0 is going to be your first line of defense. That's the first thing you try, is plugging in 0. Because great things happen with 0. Things equal 1, things equal 0, that kind of stuff. Things are undefined, so a lot of special things happen at 0. You can see here that when we let x equal 0, on the left-hand side we get 1, but on the right-hand side we get -1, and therefore that is not a trig identity. Okay, what if we want to verify that something is a trig identity? Well, that's where we have to, make sure that the two things are equal algebraically, right? We can no longer just plug in a number and see, because then we would have to plug in every single number, and there are infinitely many numbers, so that's impossible. Instead, we have to do it algebraically. If I want to prove that these two things are the same, well, I don't know about you, but when I look at that first thing here, without even looking down below at what they're doing, I think, I don't like fractions. Let's multiply both sides by cotangent, which is this, right? They didn't do it. Instead, they left it over a common denominator. Don't know why they would do that, right? I would just multiply both sides by cotangent and get this, and go, hey, that's my sine squared plus cosine squared equals one thing that's been augmented, right? It's been changed. I know that I need a cosecant and a cotangent. Well, cotangent is cosine over sine, so it sounds to me like I need to divide everything by sine squared, right? Because now this gives me 1 plus cotangent squared equals 1 over sine squared is cosecant squared. And now all we have to do is move it around, right? Subtract the 1. Cotangent squared equals cosecant squared minus 1. Ding ding! That's an identity. Okay? Another example. Well, again, a bunch of fractions. So, you can see what they're doing. I'd probably treat it a little differently. I'd probably multiply both sides by sine and cosine to get rid of the fractions, see what happens there. Or, maybe you think, well, sine over cosine is tangent. I can let that be tangent. And then secant over sine, figure out what that is. Cosine over sine, figure out what that is. But that's not really going to help you, because remember, your identities are all about squares. So tangent equaling something is not going to help you as much as tangent squared equaling something. Okay? You can follow through the steps of what they're doing here. You'll notice that as they go from step to step, they're just trying to get less and less things. Instead of 1 minus cosine squared, they can swap that out for sine squared. And then that's going to help them reduce to sine over cosine. and therefore the left side now equals the right side. Here's another example. Again, we're going to start with the most complicated side and see if we can make it look like the less complicated side. The left side is not the more complicated side strictly because it has a higher power. It's really more complicated because it's plus and minus, whereas the other one is just one piece, right? It's cotangent squared times cosecant squared. Okay, why do you think they're going to cosines and sines? Well, because everything's built on cosines and sines. So if we can make the left-hand side look like just a bunch of cosines and sines, then make the right-hand side look like a bunch of cosines and sines, we've got a good chance of then being able to see that the two sides are equivalent or not. Okay, so all of these steps was just getting it down to cosines and sines all over a common denominator. That's it. Now you'll notice that up above we have cosine squared times the quantity cosine squared plus sine squared, right? If you didn't notice it down here. See, if you can factor out a cosine squared from both pieces, you get cosine squared times cosine squared plus sine squared. And you go, aha, I remember, that's 1. Now you just have cosine squared over sine to the 4th. And when you look at the right-hand side, you notice that the right-hand side has a cotangent squared in it. So you might as well, kind of pull a cotangent squared out of this thing by taking a cosine squared and 2 of the sines. So there's your cotangent. The leftover piece ends up being cosecant, which is exactly what the other one was, right? And you go, yay, they're the same. Okay, so are you starting to see the pattern? You start with the most complicated piece, try to make it look like the less complicated piece. Oftentimes, switching everything to sines and cosines can be very helpful. And then, of course, knowing your basic identities as far as the Pythagorean ones, the sine squared plus cosine squared equals 1, and the 2 other versions of that. Those are very helpful. Here's another example where they use that. Cotangent squared plus 1 becomes cosecant squared. Here's another example, similar. Starting with the left-hand side, we recognize we have some things up here on the right that are kind of like our identities. So maybe we want to do something over here, or more importantly, we have one fraction here. We have 2 fractions here. The only way we can get these two sides to equal is if we have one fraction on the left. And the only way to do that, right, is common denominator, which in this case just ends up being the product of the 2. And because they are conjugates of each other, you just get 1 over sine squared, which by the substitution is cosine squared, and the top reduces down to 2 sine x. On the right-hand side, we just move the 1 over, right? So tangent squared plus 1 becomes secant squared. Then we get 2 secant squared over cosecant. And if we convert that, right, 1 over cosecant is sine. We get 2 sine over cosine squared, and that's what we had on the other side. So you can see oftentimes you get one side simplified down to some sines and cosines and then get the other side to do the same. Because it's really easiest to kind of see if they're the same through sines and cosines. One last example using conjugates. Again, we have one fraction equaling another fraction, so we don't have to worry about combining fraction this time, but we have a fraction on the right that just has cosine on the bottom, and we think, well, hey, if I multiply top and bottom by 1 minus sine, I'm going to get 1 minus sine squared, which is going to become cosine squared, and then hopefully some stuff on the top, right, will cancel out, and in fact it does, and it leaves me with exactly what I need to say that it's equivalent to the right-hand side. All right, in summation, what do we need to know? Algebra operations. all of this is based on knowing how to add and subtract fractions and things like that. So make sure that you are still practicing your basic algebra skills. The fundamental trig identities. You definitely need to know sine, cosine, tangent, and how the other three are equal to 1 over whatever. And then on top of that, you really need to know sine squared plus cosine squared equals 1. If you have the other two memorized, great. If not, just know that you can always derive them, right, by either dividing by sine squared or dividing by cosine squared. Okay, after that, the other stuff you need to know from this section is how to work with these identities. Starting with the more complicated side is always a good option. Staying focused on the final expression, and what that means is if you're working with the left hand side because you started with it because it was the most complicated, always keep an eye on what the right hand side is, because it kind of dictates what you think you want to do to get the left side to look like the right side. You look over there and go, hey, that's only one fraction, so I better do some stuff to make the left-hand side end up being just one fraction. Or, hey, I look over there and I see that one's got a sine on top and a cosine on the bottom, so maybe I want to do some stuff over on the left-hand side where I end up having a sine on top and a cosine on bottom. You see what I'm saying? So that's what it means by staying focused on the final expression, is keep an eye on the prize. Know where you're going. Keep an eye on that finish line. These last three techniques are not always helpful. They're really more dependent on the type of problem you're faced with, but they do come up quite a bit. Converting everything into sines and cosines can oftentimes be very helpful. Not always, but really often. That's why it's number 3. It's still a pretty strong technique. Working on both sides at the same time, yeah, really it's best to work on one by itself a little bit and then maybe work on the other a little bit and then kind of go back and forth. So if you're not able to get one side kind of where you think it's completely as simple as it's going to get, then stop and work on the other one. Sometimes it's easier to kind of work from both ends and meet in the middle and kind of see where they're both leading you to. They both tend to be leading towards a similar expression, so that can be helpful. And then last but not least is always keep your eye open for conjugates, because conjugates do awesome things, because when you multiply by conjugates you just get the square, right? You get a squared minus b squared, and because so many of our trig identities involve squares, then the conjugates end up giving us something that folds right into those Pythagorean identities. Alright, and that's everything you need to know about working with these trig identities.